Alright, so today's crash course is on acids, bases, and salts. So we'll be covering the key concepts and also the common misconceptions that most students have. Okay, so our agenda today is to cover the definition of acids, all the reactions, and also strength. Okay, whether an acid is strong or weak. Okay, then there will be MCQ and a structured question for you guys to try. Then next we'll go through bases, definition, reactions, and strength again. And then there'll be MCQ for you to try. Okay. Then next, we'll go through the 4 types of oxides. Okay, so I'll give you some memory shortcuts that you can use to remember some of these concepts. Okay, then there'll be questions again. And one of the most important part is the solubility table. Okay, so the solubility table is not only just used in this chapter, it's used in almost every chapter in chemistry. Okay, so you need to know whether a substance is soluble or insoluble. That's why we use a solubility table. Okay, then there's a structured question for you to try. Then finally, we move on to preparation of salts. Okay, this is something that a lot of students struggle with, mainly because they try to memorize. But today I'll try to explain in a way such that you don't need to memorize, okay, so that you can understand this concept. Okay, so it consists of titration, adding excess, and precipitation. Okay, then there'll be questions again. Then at the end, I'll let you know what it's like to be in our classes if you want to be. And there will be a feedback form so that we know how to improve. Okay, and then I'll answer questions you all have. Okay, so without further ado, let's begin. So acids, definition of acids. Acids are substances that release hydrogen ions when dissolved in water. So think of it like you have a cup of water, right? Okay, cup of water. Then you add a lemon. Okay, let's say I add a lemon inside. Okay, I add a lemon inside. What will happen to the water? The water will turn sour, correct? So the lemon actually spreads the sourness throughout the water. So acids are like lemons. When they enter the water, they will dissolve and then they will release the hydrogen ions. Okay, then these hydrogen ions will spread throughout the water. So it's similar to how the lemon spreads sourness across the water. Okay, so that's the definition of acids. Definition. Sorry. Definition. Okay. So general properties, they have a sour taste. So again, we use the lemon analogy. Lemons, they are sour. Okay, so acids, they are sour. And they are able to conduct electricity. Why they can conduct electricity is because once they dissolve in water, they release hydrogen ions, right? So these hydrogen ions are free to move. These hydrogen ions are free to move to conduct electricity. Okay, so that's why acids can conduct electricity. It is corrosive if concentrated. Okay, so concentrated. If an acid is concentrated, it is corrosive, and it is able to react with 3 things: metals, carbonate, and bases. Okay, so I'll go through a way to remember these 3. And finally, it can turn blue litmus paper red. Okay, so litmus paper, there are 2 colors. Blue and red. Okay, blue means it has properties of an alkali. Okay, blue means the pH is above 7. Okay, then red means the pH is below 7. It has acidic properties. Okay, so let's move on to the reactions. So I use this acronym to remember the reactions. Okay, if you guys have something to remember already, then you can ignore this. But if you don't, then I highly recommend this. So my big car accelerates. If we focus on the first 3 words, my big car, okay, M, B, and C. So M is metal, B is base, and C is carbonate. Okay, so acids react with metals, bases, and carbonate. Okay, and then one thing to note, for metals, right, it has to be a reactive metal. Reactive. Okay, so if your metal is unreactive, it's not going to react with acids. Okay, keep that in mind. Okay, then the next important part is the products form. Okay, all the products form are different. You have salt and hydrogen form when acid and metal mix together. Okay, so let me give you an example. Okay, let's say sodium. Okay, sodium and hydrochloric acid. Okay, so sodium is your metal. In your periodic table, sodium is in group 1. Okay, so it's a metal. And then hydrochloric acid is an acid. Okay, so it will give you salt and hydrogen. So what exactly is a salt? A salt is basically when your acid, right, is the hydrogen of the acid is replaced by the metal. Okay, that means this hydrogen is replaced by sodium, so it becomes sodium chloride. Okay, then once you have sodium chloride, what is left? You left hydrogen. So this hydrogen will of course be hydrogen. So H2. Okay, wait, let me make this smaller. So you have Na plus HCl will give you NaCl plus H2. Okay, then you just have to balance the equation. Okay, thing is balanced. Yeah. So you don't have to remember acid plus metal give you salt and hydrogen. Just by writing a formula like that, you automatically get a salt, and then what is left is hydrogen. Okay. So there's a way to test for hydrogen. You place a lighter splint at the mouth of the test tube where the reaction is happening. And if hydrogen is present, then there will be a pop sound. Okay, it will extinguish a pop sound. Okay, next, M is metals, so B is base. So reaction with base. This acid plus base will give you salt and water. Okay, so pretty straightforward. This is also called a neutralization reaction. So why is it neutralization? Think of it like you know firefighters, right? Firefighters, they neutralize the fire. Okay, so the firefighters are your alkali, they are your base, and then the fire is your acid. Okay, so the firefighters will neutralize the acid. So the bases neutralizes the acid. That's why the whole reaction is called neutralization. Okay, then salt and water will be formed. Okay, then the third reaction is with carbonate. Okay, so specifically metal carbonates. So acid plus carbonate will give you salt, water, and carbon dioxide. So it's obvious, right? You have a carbonate, then the product you have carbon dioxide. So both have carbon. Okay, so that's how I remember the products. So for metals, you'll get hydrogen because it's the last one remaining. Then for base, because it's neutralization, you get salt and water. And then for reaction with carbonates, because you have carbon, you will form carbon dioxide. Okay, so salt, water, and carbon dioxide. So how do we know like these reactions occurs, right? Is based on the testing of the gases. So how do we prove that this acid react with this metal? Is to test for hydrogen. How do we prove that this acid react with this carbonate? Is to test for carbon dioxide. So how do you test for carbon dioxide? You bubble the gas form into lime water. Okay, then there will be a white precipitate form. There will be a white precipitate form in lime water if carbon dioxide is present. Okay, so I don't know if you guys know, but lime water is actually calcium hydroxide. Okay, lime water contains calcium hydroxide. Then the white precipitate is actually calcium carbonate. Okay. So the white precipitate is calcium carbonate. And then the lime water is calcium hydroxide. So basically the calcium hydroxide, why we use lime water is because the calcium hydroxide reacts with carbon dioxide to form calcium carbonate, which is your white precipitate. Okay, so these are the three reactions. So this is my big car. Then what about accelerates? So accelerates is basically for later. It's one of the reactions that bases have. So M, B, and C is for acids. Then accelerate is for base. So later I'll go through that part. Okay, now we move on to the strength of an acid. So a strong acid, it will ionize fully in water to produce hydrogen ions. A high concentration of hydrogen ions. Okay, then a weak acid, it will ionize partially, only to give a lower concentration of hydrogen ions. Okay, so for example, again, I have a cup with water. Then let me just think of a random acid. HCl, the most common one. Okay, then I add HCl inside. So hydrochloric acid is actually a strong acid. These three acids are all strong. Hydrochloric, sulfuric, and nitric. These are the three acids that you most commonly use, and they're also your strong acids. So strong acids, they will ionize fully, right? So it will turn into H plus and C. So the whole HCl molecule, it will turn into H plus ions and Cl minus ions. Okay, it will completely turn into ions. That is a strong acid. What about weak acid? This is a weak acid. Huh? Okay, I'll just use hydrochloric acid as an example again because it's easier. Okay, but remember hydrochloric acid is a strong acid. Okay, now I'm going through weak acid. So here is weak. This is strong. Okay, again, it will ionize to form H plus and Cl minus ions. Correct? But not completely. That means maybe only half of the HCl will turn into H plus and Cl minus ions. Then the other half, right, it will remain as a molecule. That means the other half will remain as a HCl molecule. Then another half will dissociate or ionize to become ions. So that's what it means by ionizing partially. Okay, so ionized partially is weak acid. Ionized fully is strong acid. Okay, and then examples of weak acids are your organic acids. Okay. So question 1. Dilute sulfuric acid is added to separate samples of solid substances. Okay, so the acid is added to solid substances. Which row is correct? Okay, so the key, it is a tick if there's a gas involved, and it is a cross if there's no gas involved. So if we look at this table here, right? Okay, it's a bit messy, but there are only two reactions that give you gases. One is the reaction with metal because it gives you hydrogen. Okay, then the second one is the reaction with carbonates, which give you carbon dioxide. Okay, so in this answer, I'm looking for ticks for metals and carbonates. Then I'm looking for crosses for those that are not metals and carbonates. Okay, so we have copper, magnesium, and sodium carbonate. Now, copper, would there be a reaction with dilute sulfuric acid? Actually, there won't be any reaction because copper is unreactive. Okay, remember I said acids, they have to react with a reactive metal in order to form salt and hydrogen. So because copper is unreactive, there will be no reaction. Okay, there will be no reaction and therefore there won't be any gas involved. So we can cross out options A and B. Okay, then second option, magnesium. Okay, magnesium is a reactive metal. So when it reacts with sulfuric acid, it will definitely form hydrogen. Okay, so it's a tick, which means C is your answer already, just by eliminating. Okay, but I'll just go through the rest. Zinc oxide, it is a base. So acid plus base, what do you get? Acid plus base, you get salt and water. So water is not a gas, it is liquid, and salt is also not a gas. So there won't be any gas, so it's a cross. And then finally, you have carbonate, sodium carbonate. Okay, so acids plus carbonates, you get salt, water, and carbon dioxide. So carbon dioxide is a gas, therefore it should be a tick as well. So your answer is C. Okay, so those people who put A, remember copper is unreactive, so it cannot react with another acid. Okay, then we move on to question 2. Okay. So we have this table here showing your acid and the concentration of H plus ions present in the solution. Okay, so it's 1, 1, and 2 mole per dm cube. So suggest why sulfuric acid has a higher concentration of H plus ions present in the solution compared to nitric acid and hydrochloric acid. So if you remember what I said, all three of these, right, they're actually strong acids. So what could make sulfuric acid have double the amount of concentration? It's actually the formula of the compound. Nitric acid is HNO3. Okay, this is the chemical formula of nitric acid. Okay, let me use red color. Okay. Then hydrochloric acid is what? HCl. Sulfuric acid, H2SO4. Okay. So do you see a difference between the three? I mean, between sulfuric acid and the other two acids? The number of hydrogen atoms. So in nitric acid and hydrochloric acid, there's actually only one hydrogen atom. Okay. Then in sulfuric acid, there's two hydrogen atoms. So what happens is it will dissociate in water. Okay, all the acids here are strong, right? So all the acids will dissociate fully in water. But sulfuric acid, since it has 2 times the amount of hydrogen atoms, it will dissociate in water to form double the concentration of hydrogen ions. So this is your answer. Since sulfuric acid has 2 hydrogen atoms, while nitric acid and hydrochloric acid only has 1 hydrogen atom in the formula, sulfuric acid will dissociate or it will ionize fully in water to form double the concentration. Okay, forgot to add the word fully. Fully in water. Yeah. Okay. So all of them are strong acids, but sulfuric acid has 2 times the amount of atoms, hydrogen atoms. So it will form double the concentration of hydrogen ions. Okay, so the question has 2 marks. The first marks comes from saying that sulfuric acid has 2 hydrogen atoms, while the other 2 acids have 1 hydrogen atom. Okay, then the second mark comes from saying it will ionize fully to form double the concentration. Is the term for this dibasic? No, it's not dibasic because these are acids. Right? Acids, they are not basic, they are acidic. So there's not really a term for this. It's just that the same amount of acid will dissociate fully, but to form double the concentration because it has double the atoms. Okay, there's not really a term for this. So definition of bases. Bases are metal oxides that react with acids to produce salt and water. Okay, so we already learned the reaction. Acid plus base give you salt and water. This is your neutralization. So bases are basically just metal oxides, which means metal plus oxygen combined together. Okay, so it can form a compound. Okay, examples of bases. So since they are your metal oxides, of course you need metals. So iron 2 oxide is one of them. Magnesium oxide is another type of base. Okay, so really metal oxides. Okay, so most bases are insoluble except a few. So except your group 1 metals and your ammonium ion. Okay, so I'll actually go through this in the solubility table as well. But here it already says most bases are insoluble except for bases in group 1 metals or ammonium ion. Okay, so those bases that contain these metals in group 1, they are soluble. Okay, definition of alkalis. So if you guys didn't know, bases and alkalis are actually different. Bases are basically just metal oxides, but alkalis are metal hydroxides that can release hydroxide ions. Okay, so that they are soluble bases basically. Yeah, so alkalis are the one that are soluble in water, so that they can release hydroxide ions when dissolved in water. So it's pretty similar to acids, but the only difference is it releases hydroxide ions, OH minus. Okay, so that's the definition of alkalis. So the general properties of alkalis, it has a soapy feeling. It turns red litmus paper blue. Okay, remember I say litmus paper, that's red and blue. Blue is for the alkali properties. Okay, so it turns red litmus paper blue. It's able to conduct electricity because there are the hydroxide ions formed when it's dissolved in water. Okay, these hydroxide ions can move around to conduct electricity. Again, just like acids, it's corrosive if it's concentrated, and it can react with acids to form salt and water. So this is your neutralization that we just learned. Okay, and there's a new property, which is reaction with ammonium salts to form ammonia, salt, and water. So remember this acronym I gave, my big car accelerates. Now this is where we use accelerates. So M, B, and C was from acids. Now we use the A. Okay, A is your ammonium salts. So base or alkali plus ammonium salt will give you salt, ammonia, and water. Okay, let me give you an example. Okay, let me paste it in. So we have a base or alkali, which is sodium hydroxide plus ammonium salt. So ammonium salts are basically salts that contain the ammonium ion. So for example, ammonium chloride, ammonium sulfate, ammonium nitrate, these are all ammonium salts. Okay, so in this example, I use ammonium chloride. So your base or alkali plus ammonium chloride will give you salt, ammonia, and water. So ammonia and water will always be the same. Ammonia is NH3 and water is H2O. The only difference is the salt. So how do you work out the formula of the salt? We look at the ammonium chloride. Okay, so we're basically going to replace this ammonium ion, which is the NH4. We're going to replace it with the metal in the alkali. So what's the metal in the alkali? Sodium. Okay, so sodium is going to replace this ammonium ion. Therefore, this salt will become sodium chloride. Okay, so that is how you form the equation for reaction with ammonium salts. Okay, then again, right, since there is a gas form, there's actually a test to prove that ammonia is formed. Okay, to prove that this reaction happened. So you put a damp or moist red litmus paper at the test tube or wherever there's a presence of NH3 gas, because it's an alkaline gas. So what will the red litmus paper turn to? It will turn to blue. Okay, it will turn to blue if ammonia gas is present. Okay, and it's important that this red litmus paper is damp, because we learned that alkalis release hydroxide ions when dissolved in water. So only when it touches the water, then it will release the hydroxide ions. And these hydroxide ions are what cause the red litmus paper to turn blue. Okay, so that is your reaction. Okay, strength of an alkali. Same thing with acids. Strong alkali will ionize fully, but this time is to produce a high concentration of hydroxide ions. Okay, then a weak alkali, it will ionize partially, only to give a lower concentration of hydroxide ions. Okay, so it's similar to acids. It's just different ions form. Okay, for acids, it was hydrogen ions. For alkali, is hydroxide ions. Okay, I'll be going through the questions now. So question 3, the diagram shows two substances, R and S, being heated together. Okay, so which row is correct? Okay, then there's a damp universal indicator. Okay, so for universal indicator, I like to use this acronym, which is Roy G Beef. Okay, so G is basically green, and it's in the middle of this acronym. So it's when the pH is neutral, when the pH is 7. Okay, then below green is your red, orange, yellow, and then above is your blue and purple. Okay, so it's actually blue, indigo, violet, but I just remember it as purple. Okay, so blue, purple is alkali properties, then red, orange, yellow is acidic. Okay, then green is neutral. So let's look at the options. First, you have ammonium chloride and equals sodium hydroxide. So ammonium chloride and aqueous sodium hydroxide is actually one of the reactions we just learned, which is a alkali plus ammonium salt. Okay, ammonium chloride is your ammonium salt, and then aqueous sodium hydroxide is your alkali. So they'll react to form salt, ammonia, and water. Okay, particularly ammonia. So ammonia is formed. It's formed. And ammonia is an alkali gas, which means that it will have properties of an alkali. So it will turn the universal indicator, it will turn it blue. Okay, so A is actually correct because it shows that ammonia has the properties of an alkali. So A is the answer. Okay, but let's go through the rest. So we have ammonium chloride and hydrochloric acid. So ammonium chloride, hydrochloric acid. We didn't learn any reaction for this. Okay, because acids, we only learn 3, right? Acid plus metals, acid plus base, acid plus carbonate. We didn't learn acid plus ammonium chloride. Okay, so there won't be any reaction, and therefore there won't be any gas. Okay, there won't be any gas form. Remember, they're heating this, right, so that the gas form can travel upwards to reach the universal indicator. But we didn't dip the universal indicator into the substances. We leave it at the mouth of the test tube. Okay, so the only way for the universal indicator to change color is if a gas travels up. Okay, so if there's no gas form, then there's no way it's going to change color. Okay, because it didn't physically touch the liquid. Okay, if it physically touched, then it will turn red because of hydrochloric acid. But since it didn't physically touch, it's at the mouth of the test tube and no gas is formed, there will be no change. Okay, this one is no change. No change. Okay, third reaction. Aluminium and aqueous sodium nitrate. So aluminium is a metal. As you can see in the periodic table, aluminium is here, so it's a metal. And then aqueous sodium nitrate is a metal nitrate. But we didn't learn any reactions involving metals and nitrates. Okay, we didn't learn yet. So there's no gas form. Since there's no gas form, the universal indicator will have no change. Okay, so B and C are out already. And then the last option, D. We have aluminium again, which is a metal, and hydrochloric acid. This is a familiar reaction, right? We have learned this. This is metals and acids. Okay. Acid plus metal. What does it give you? Salt and hydrogen. Hydrogen is neither acidic nor alkaline. Okay, it's a neutral gas. So it won't turn the universal indicator red. Hydrogen is neutral. Okay, so there'll be no change. And therefore your answer is A. Okay, because A, it forms ammonia, which turns the universal indicator blue. Okay. So your answer is A. Then now we move on to question 4. Okay, a flask contains copper 2 oxide. Pure water and a universal indicator are added to the flask. What is the color change of the universal indicator? Okay, so firstly, copper 2 oxide is a base, but it is insoluble. Insoluble. Okay, pure water and a universal indicator are added. So what is the color change? So for a universal indicator, in its original state, it is green in color, right? Because it's neutral. So before it has to be green, cannot be red. Okay, then you have A, B, and C. Okay, pure water, right? Pure water is neutral. Pure water is neutral, which means it's not acidic and it's also not alkaline. Okay, but will copper 2 oxide dissolve in the pure water to form an alkali? No, right? Because copper 2 oxide is insoluble. Remember, we mentioned that most bases are insoluble except bases with group 1 metals, and ammonium ion. Okay. So since copper 2 oxide is insoluble, the pure water, the universal indicator is basically measuring the pH of the pure water only. Okay. So it's green, after is green also. The answer is B. So there's no change in the universal indicator color. Okay. So if there are no questions, I'll move on to types of oxides. Okay. If no questions, please give me a reaction. Okay, nice. All right, now we will move on to the types of oxides. Okay, so there are 4 types of oxides. We have basic, amphoteric, acidic, and neutral. So I remember this using just a random acronym called ABAN. Okay, or ABAN, whatever. So A is amphoteric, B is basic, A is acidic, and N is neutral. Okay, so we have these 4. And we can actually split these 4 oxides into 2 groups. Your first group is metal oxides. And then your second group non-metal oxides. So your basic oxide and your amphoteric oxide, A and B, basic and amphoteric, they are your metal oxides. Okay, then your acidic oxide and neutral oxide, A and N, they are your non-metal oxides. Okay, which means metal oxides is metal and oxygen combined. Then non-metal oxides is non-metal and oxygen combined. Okay, so we'll start with basic oxide. We'll start with amphoteric oxide. So we Singaporeans, we are bilingual. We are mostly bilingual people, right? Because we speak English and a mother tongue language. So we can communicate in 2 languages, most of us are. Amphoteric oxides are the same. They can react with 2 things, acids and bases. Okay, they can react with both acids and bases. So they're very special. They are like bilingual people. They react with both acids and bases. And there are only 3 types of amphoteric oxides that we learn in our syllabus. ZEP. Okay, use this acronym ZEP. So Z is zinc oxide. A is aluminium oxide. P is Pb, which is lead 2 oxide. Okay, so zinc, aluminium, lead 2 oxide, these are your amphoteric oxides. Okay, so remember this. And all these oxides, right, lead 2 oxide, aluminium oxide, and zinc oxide, they can react with either acids or bases to form salt and water. Okay, so they are your very special kind of oxides that can react with both acids and bases. Okay, and they are your metal oxides also. So remember I mentioned that basic oxides are also metal oxides. So all metal oxides except for these 3, zinc, aluminium, and lead, they are basic oxides. Okay, simple to remember, right? Amphoteric is Z, and then basic is everything except for Z. Okay, and then they're all metals. So examples, you have copper 2 oxide, sodium oxide, and magnesium oxide. Okay, and basic oxides, they will have the same properties as a base. Okay, they will have same properties as base, which means it can also react with acids. Remember neutralization? Base and acids form salt and water. Okay, so it reacts with acids to form salt and water, just like how a base reacts with acids. Okay, then we move on to your non-metal oxides. Okay, so they look quite similar. They are basically non-metal and oxygen together. But how do we differentiate neutral oxide and acidic oxide? You see here we have carbon, right? But here we also have carbon. So how we differentiate the two? Neutral oxide usually has only 1 oxygen atom. Okay, neutral oxide only has 1 oxygen atom. if we look at the chemical formulas, right, CO, which is your carbon monoxide, okay, monoxide already says it has one oxygen atom, okay, mono, one oxygen atom, okay. Then water H2O, it also has one oxygen atom. So these non-metal oxides with one oxygen atom are your neutral oxides, okay. Then acidic oxides is basically the same thing, but two or more oxygen atoms. Okay, if you have a non-metal and two or more oxygen atoms, they are your acidic oxides. So example, carbon dioxide, sulfur dioxide, phosphorus oxide, all these have two or more oxygen atoms, right? You see, CO2, SO2, and P2O3. It all is two or more oxygen. So that's how you differentiate acidic and neutral. Okay, then for the reaction, same thing. Acidic oxides, they will have the same properties as acids. So they will react with bases to form salt and water. Okay. Neutral oxides, on the other hand, it will have no reaction with anything. So no reaction with acids, no reaction with bases. Okay. So let me go through again. Amphoteric oxide is Zep, zinc, aluminium, and lead. Okay. It reacts with both acids or bases. Then basic oxides, they react with acids only. Acidic oxides, they react with bases. And neutral oxide, they react with nothing. Neither acids or bases. Okay, I'll now go through the questions. Question 5. An aqueous solution of sodium hydroxide has a pH of 10. Which compounds could be added to aqueous sodium hydroxide to decrease the pH? So we have sulfur dioxide, we have carbon dioxide, and we have calcium oxide. Okay. So in order for the pH to decrease, the oxides have to be below 10. Okay. Have to be below 10. And it also has to be able to react with the aqueous solution of sodium hydroxide. Okay. So we start with sulfur dioxide. Sulfur dioxide, the formula is SO2. Okay. So sulfur in the periodic table is over here. So it's definitely a non-metal. So it's between acidic and neutral oxide. Okay. But since there are two hydrogen atoms, we know that is an acidic oxide. Okay. So acidic oxide, it can react with sodium hydroxide because sodium hydroxide is an alkali. Okay. Acid plus alkali, right? To give you salt and water. So that will decrease the pH because acidic oxides, the pH is below 7. Okay. So this is acidic. So it's correct. Okay, then number 2, carbon dioxide. Carbon dioxide is CO2. Okay, it is another non-metal oxide which contains 2 oxygen atoms, which means it's also an acidic oxide. So again, acidic oxides, it can react with alkali to reduce the pH. Okay, so 1 and 2 is correct. Okay, next, calcium oxide. So calcium oxide is a metal oxide because calcium is group 2. Group 2 elements are metals. So it is alkali. Sorry, it is a basic oxide because it is not one of the Z. It's not zinc, aluminium, or lead. Okay, so it's basic. Now I want you guys to think about this. It can be basic but below pH of 10. Correct? So as long as below 10 can already. But one thing that calcium oxide doesn't fulfill is that it's insoluble. Sorry, not insoluble. It cannot react with sodium hydroxide. Okay, we learned that basic oxides, they only react with acids to form salt and water. Okay, they don't react with other alkali. Therefore, this thing cannot react with sodium hydroxide. So the pH will remain the same even if you add it. Okay, so your only options are 1 and 2. Okay, so B, C, and D is out. Your answer is A. Okay. Question 6. Okay, an unknown hydroxide is a white powder which is insoluble in water. Using name reagents, describe how you could show that this hydroxide is amphoteric. Okay, so we have to use name reagents. So amphoteric oxides, they can react with either acids or bases, right? Remember I said they are like bilingual people. We can communicate in two languages. Amphoteric oxides can react with acids and bases. Okay, so we just have to add a name reagent that is an acid and another name reagent that is an alkali and see if there's a reaction. Okay. So those reagents that I accept are hydrochloric, nitric, and sulfuric acid. Okay, so it reacts with or it dissolves in hydrochloric acid or sulfuric acid or nitric acid. So you just choose one. And it also reacts with sodium hydroxide or potassium hydroxide. So any strong acid or strong alkali, you can use it as a name reagent. Can you re-explain why calcium oxide is not? Okay, calcium oxide is not an option. Firstly, because it is a basic oxide. Okay. Sodium hydroxide is a pH of 10, right? So if you want to decrease it, it needs to have a pH below 10. That's the first thing. But because it cannot even react with sodium hydroxide, right? Basic oxides, they only react with acids to form salt and water. If it cannot even react with sodium hydroxide, it cannot change the pH of sodium hydroxide. Okay, so first thing is that it's basic. Second thing is that it cannot react with sodium hydroxide. Because there's no reaction, it cannot possibly change the pH of sodium hydroxide. Okay, so the sodium hydroxide will still have a pH of 10 even after you add calcium oxide. Does that answer the question? Your question? All right. Then we'll move on to solubility table. Okay, this is the most important part, or one of the most important part. Okay, because it will help you with your other chapters as well, regardless of Sec 3 or Sec 4. Okay. Right. So if you look at this table, we have a few different types of salts. We have the nitrate, sulfate, chloride, and then oxide, hydroxide, and carbonate. Okay. So you have soluble and you have insoluble. So everything in this row is soluble, everything in this row is insoluble. Okay. So firstly, nitrates. All nitrates, all metal nitrates, they are soluble. Okay, so whenever you see a nitrate, right, something nitrate, 100% is soluble. Okay, it will never be insoluble. Okay, so it's all soluble in water, which means that if you add water to a certain nitrate, it will turn, the thing will turn aqueous. Okay, which is this state symbol. Okay, now we move on to the confusing part, which is sulfate and chloride. So I have a acronym for this. Let me copy and paste it. So for your insoluble sulfates and chlorides, I use this acronym. Let two salts can be lethal. Okay, so we look at the first two words, lead and salts. L and S. L is for lead, S is for silver. Okay, so lead 2 chloride and silver chloride, they are insoluble. Okay, so lead 2 chloride and silver chloride, they are insoluble in water. Then everything else, all the other chlorides, they're all soluble. Okay, then next we have can be lethal. So can be lethal, we have C, B, and L. Okay, C is for calcium, B is for barium, L is for lead. So your calcium sulfate, lead 2 sulfate, and barium sulfate, they are all insoluble. Okay, so these are the 5 insoluble salts that you really have to remember. Okay, so I use this term, lead 2 salts can be lethal, to remember. Okay, so L and S is for chloride, C, B, and L is for sulfate. Okay, then if none of the chloride or sulfate falls under these letters, it means that it's soluble. Okay. Okay, then one more thing I want to add in is for oxides, hydroxides, and carbonate. Okay. So most of your oxides, most of your hydroxides, and most of your carbonates, they are insoluble. Those that are soluble are from group 1. They contain group 1 metals or the ammonium ion. Okay. So copper 2 oxide. Copper is not group 1 and it's not ammonium. Okay, that means it's insoluble. So copper 2 oxide, copper 2 hydroxide, and copper 2 carbonate is insoluble. But if I give you sodium oxide. Sodium is actually from group 1, right? If we look at the periodic table, sodium is here, group 1. Okay, so it's soluble. So sodium oxide, sodium hydroxide, sodium carbonate, they're all soluble. Okay, then also ammonium. Ammonium oxide, ammonium hydroxide, and ammonium carbonate, they are all soluble in water. Okay, so I really encourage you guys to understand this solubility table because it will help you in your other chapters as well. Okay, especially writing equations to know whether the state symbol is correct. Okay, I'll go through the question now. Question 7. Some metal ores contain gold mixed with impurities, which include compounds of lead. Okay, dilute hydrochloric acid or dilute sulfuric acid cannot be used to remove these compounds of lead. So explain why we can use dilute nitric acid, but we cannot use the other two acids. So they're all acids, right? And they're all strong acids. The only difference is the elements that it contains. So hydrochloric acid, it contains chlorine. Sulfuric acid, it contains SO4, which is sulfate, the sulfate ion. SO4 2-, okay? Then when it reacts with lead, right, it actually forms lead-2 chloride and lead-2 sulfate. Okay, if we look at the solubility table, right, for sulfates and chloride, lead-2 sulfate and lead-2 chloride, they are all insoluble in water. So what happens if you add it to lead? Let's say you have a piece of lead here, and then you add your dilute sulfuric acid, add your dilute hydrochloric acid. So you add already, then it will react for a while. Yeah, it won't be completely no reaction. It will still react for a while until it forms a layer of lead-2 chloride and lead-2 sulfate. So this layer is actually insoluble, right? They are insoluble salts. So it will form a layer around the lead. And this layer will prevent the reaction from continuing. Okay, because there's a layer around the lead, it's like it acts as a barrier to stop the reaction. So since it stops the reaction halfway, they are not reliable ways to remove the compounds of lead. Okay, whereas dilute nitric acid, when it reacts with lead, it forms lead-2 nitrate. And remember, all nitrates are soluble, so it can be used to remove the lead. So the answer is just what I said, but put into words. Dilute nitric acid, it reacts with lead to form a soluble salt. Okay, because all nitrates are soluble, which can be easily removed from the gold by filtration. Remember, at first you have gold, right? And gold contains the impurities, which contains lead. So once the lead is removed, there will be a solution here. So you have to remove the solution by filtering it out. Okay, but both hydrochloric acid and sulfuric acid, when they react with lead, they will form what? The insoluble layer, right? Because lead-2 chloride and lead-2 sulfate, they are insoluble. So it will form a layer around the lead, and therefore it causes the reaction to come to a stop. Okay, because the layer acts as a barrier to stop the reaction. Okay. Is this the same as aluminium oxide insoluble layer? Yes, it's the same. As long as it's insoluble in water, there will be a layer formed, right? And you look at aluminium oxide, we compare it to the solubility table, right? For oxides, they are mostly insoluble except for group 1 and ammonium. Okay, but aluminium is in group 13. So that's why it is insoluble. Okay, so there will be an insoluble layer of aluminum oxide if aluminum reacts with oxygen. Yeah. All right. Now the final part, preparation of salts. So many students actually find this very daunting, but I'm going to try to explain it in a way that you guys don't have to memorize but can understand the preparation of salts. Okay. So firstly, for preparation of salts, there are 3 different methods. So how do you identify which method to use if the question gives you a salt? So they tell you prepare this salt, you have to know which method to use already. So first you ask a question 1, which is the salt soluble or insoluble? Okay, if the salt is insoluble, okay, by the way, you use the solubility table to determine this. If the salt is insoluble, immediately the method you're going to use to prepare it is precipitation. Okay, if the salt is soluble, you ask question 2. Does the salt contain group 1 or ammonium ions? If it does, you're going to use titration to prepare this salt. If it does not, you're going to use any excess. Okay, so this is a simple way to determine which method you're going to use. Okay, I repeat again. If the salt is insoluble, you use precipitation. If it's soluble, you ask, does it have group 1 or ammonium ions? If it has, you use titration. Okay, so group 1 is like your potassium, your ammonium. Okay, group 1. Then if it doesn't, if it's copper, magnesium, anything not from group 1, then you use any excess. All right. So now that we understand this, I'm going to move on to the first method, which is titration. So this method is suitable for producing soluble salts which contains group 1 ions and ammonium ions. Okay, remember, soluble salts which contains group 1 and ammonium ions. So we look at the first example, which is sodium chloride. So do you guys drink bubble tea? How many of you drink bubble tea? Give me a reaction if you drink bubble tea. You all drink bubble tea, right? So how are when you go to a bubble tea store, let's say you are a regular at the place, right? How are they able to make it so consistently good? It's because they use the same volume of everything. So for bubble tea, right, let's say you want 50% sugar. They will always use the exact amount of sugar. Okay. Then let's say you want large size. Large size is also always the exact amount of milk tea, right? The exact amount of ice, exact amount of milk tea, and the exact amount of sugar. That's why they always produce a consistent bubble tea. So making bubble tea is like titration. You have your acids and the alkali, right, to mix together, but you want the exact volume that makes that makes a pure substance. Okay, that makes a pure salt, which in this case is sodium chloride. Okay, so in titration, your reactants are acids and alkalis. Okay, both are soluble. For this example, we use sodium hydroxide and hydrochloric acid. Okay, so hydrochloric acid, they are soluble, sodium hydroxide is soluble. Okay, so we want to find the two exact volumes of hydrochloric acid and sodium chloride in order to make a pure sample of sodium chloride, which means there will be no impurities. We have to find the exact volume. If not, there will be impurities, right? So the first step is to use a pipette, okay, to find the fixed volume of hydrochloric acid. So for pipette, right, it's usually to measure a extremely fixed volume. So like 20.0 cm cube or 25.0 cm cube. Okay, the volume will be fixed there at 20 or 25. Usually we use 25 lah. Okay, so and then it will be put in a conical flask. This conical flask is where all the magic happens, where all the reaction happens. Okay, then the second step is to add 2 or 3 drops of your indicator. Okay, so don't be confused by this word phenolphthalein. It's just another indicator lah. So the reason why we add the indicator is to see the color change, to know that the reaction is done. Okay, and one important note here, you cannot use universal indicator. Cannot use universal indicator because it gives you a variety of colors. Okay, at different pH values, it gives you a variety of colors. So you cannot see the distinct change in color. So don't use universal indicator. Okay, then the third step is to titrate drop by drop the alkali. So in this case, the alkali is sodium hydroxide. You titrate it drop by drop from the burette into the acid. Okay, so this is your burette. Titrate it into the conical flask. Okay, and your burette measurements are in 2 dp. Okay, then for pipette measurements is to 1 decimal place. Okay, then as you add drop by drop at a time, you swirl the solution such that everything is mixed. And then you keep adding slowly, slowly, slowly until you see the first appearance of color change. So for phenolphthalein, right, the color change is colorless to pink. Okay, so in acid, it will be colorless. And then once it becomes neutral, it will become pink. So once you see the pink color, stop the titration. So you stop the titration because that is the exact amount of sodium hydroxide you need to make pure sodium chloride. Okay, you're finding the exact volume of two things here. Okay, the first fixed volume is your hydrochloric acid, 25.0. Then the second fixed volume is you're measuring it from the burette. So you add until you see color change. Okay, then once you see that, note the volume of sodium hydroxide used. So take down the volume and then repeat the experiment using the exact volume of hydrochloric acid and sodium hydroxide without using the indicator. Okay, because the indicator will contaminate the solution. Okay, we don't want that, right? We want the pure sodium chloride. So we don't want any contamination. Okay, so we repeat the experiment without the indicator. Then once we're done, what are we left with? We're left with the sodium chloride solution, right? Because we add acid and alkali, right? They are both already dissolved in water. So you add together, you have a solution of sodium chloride. But if we want the pure dry sample of sodium chloride, we need to heat it. So heat the solution until it's saturated. Saturated means very little water remaining. Okay? So it's a very saturated just means very little water remaining. So you heat it until very little water is remaining. You don't heat it until all the water is gone. Because if you heat it until all the water is gone, the sodium chloride might decompose already due to the strong heating. Okay. Then after you heat until it's saturated, you let it cool so that the crystals can be formed. Okay, then the last step is always the same. You wash it with water and you let it dry, or you use filter paper to dry it. Okay, so you see it's like 1, 2, 3, 4, 5, 6, 7, 8 steps, right? But you don't have to memorize all the steps. You just have to think about you're making bubble tea, right? The acid is your milk, and then the alkali is your tea. Okay, the milk is a fixed amount. Then you're going to measure how much tea you're going to add in. By doing that, you need to add the indicator first, so you can see the color change. Okay, then you start adding bit by bit the tea until you see the color change. Then you note the volume of the tea, which is your alkali. Okay, then you repeat without the indicator and you heat the solution until it's saturated. Okay, then you let it cool so that the crystals can form. Then you wash it with water and let it dry. Okay, that is for titration. For preparation of salts, can we use the glass rod to test whether the solution is saturated? So you don't really have to test whether the solution is saturated. You can just see whether almost all the water is gone. If almost all the water is gone, then it's saturated already. Okay, or just make sure there's like a little bit of water left, not completely dry, then it's considered saturated. So I hope you guys understand titration better. Then let's move on to the second one, adding excess. Okay, just a recap here. We use adding excess to prepare soluble salts that are not in group 1 or ammonium. Okay, so the reactants for this will be acid plus acid. Okay, the reactants for titration are acid and alkalis. Okay, then the reaction for adding excess is acid and insoluble salt. Okay, so you have acid and you have an insoluble salt. So the example they gave us was copper 2 sulfate. So copper 2 sulfate is soluble, and copper is not in group 1, right? Copper is here, it's not in group 1. So that's why we use adding excess. Okay, so this reaction is actually simpler because we don't have to measure out the exact amounts. We can just add excess. Why we can add excess? Because this is an insoluble salt, which means it will not dissolve in excess. Okay. So if you look at the diagram here from left to right, I'm going to go through this now. First, you have a beaker, then you add the two reactants in. So the reactants we're using here today is copper 2 oxide and dilute sulfuric acid. Okay, we have an acid, which is dilute sulfuric acid, and we have an insoluble salt, which is copper 2 oxide. Okay, so you add them together and then you add excess copper 2 oxide. So the one you're adding in excess is always the insoluble salt. Okay, remember that. Then you stir the mixture until there is excess of copper 2 oxide left. Okay, so that's the first step. So this is to make sure all the acid is used up. All this sulfuric acid is used up. Okay, then we know that we have our copper 2 sulfate solution. Okay, so once the mixture is done, you're left with copper 2 sulfate solution and excess copper 2 oxide. Okay, this one is excess. So what do you do to remove the copper 2 oxide? You filter it. Correct? You filter so that you have your copper 2 sulfate solution. Okay. Then what do we do when we have the solution? It's always the same, right? Once you have a solution, the rest of the steps is the same as titration. Okay, so until here, it'll be the same. So you heat the solution, the filtrate, until it becomes saturated. Okay, which means very little water remaining. So once it becomes saturated, you let it cool so that the crystals can be formed. Okay, then you wash the crystals with a bit of distilled water and then you let it dry. Okay, so this and this is the same as this one. Okay, the only difference is this time you add excess you add excess insoluble salt to the acid. Okay, then you filtrate, then you filter the mixture. Okay, then the ending is the same. You heat it until it's saturated. Saturated means very little water remaining, and then you let the solution cool slowly so that bigger crystals can be formed. Okay, then you wash it with water and let it dry. All right, then I'll move on to precipitation. Okay, so this is the easiest one out of everything. Because you are preparing an insoluble salt, right? So you just have to mix two things together to form an insoluble salt. Then you just remove the two things after you form the insoluble salt. So when do we use precipitation for insoluble salts? For example, we have silver chloride. If we look at the solubility table, silver chloride is insoluble. Okay, so this is when we know we need to use precipitation. So right here, we use precipitation to prepare insoluble salts. Okay, so what's the process like? You can have two types of reactants. Either soluble salt and a soluble salt. Two soluble salts react together to form an insoluble salt. Okay, or you can have soluble salt and a dilute acid. Acid plus soluble salt react together to form another insoluble salt. And this insoluble salt is also known as your precipitate. Precipitate. Okay, so precipitate means insoluble salt. Okay, so the steps are very simple. You add to prepare silver chloride, you need either soluble salt and or soluble salt and dilute acid, right? So in this case, they chose silver nitrate and one of these, hydrochloric acid, for example. So you add your hydrochloric acid and silver nitrate together and just mix. You stir it, okay, in a beaker. Then what happens is the silver chloride will be formed as a white precipitate, okay, as a precipitate. And what will be left? The solution, right? There will be water because these two are aqueous. So what you do after you stir, you filter out. You filter out the remaining substances away. Okay, then you'll get your pure silver chloride. So for precipitation, it's very easy because you don't need to heat it. You don't have to heat the solution until saturated. Okay, then you don't have to let it cool or dry. Right? Once you mix it, you filter it, then you got it already. Okay. So for precipitation, you just mix, filter, and you got your product. All right, I'll be going through the questions now. So question 8, a salt can be prepared by adding excess solid X to an aqueous solution of Y. Excess solid X equals solution of Y. This already tells you that they are using excess, adding excess. Okay, so a solution and some solid X remain. The mixture is filtered, the filtrate is evaporated to form a concentrated solution. Okay, you have to evaporate it because it originally has water, right? It's evaporated to form a concentrated solution or saturated solution. Okay, so this double confirms that this method is adding excess. So what salt can be safely prepared using this method? The salt has to be soluble, and it has to not contain group 1 or ammonium. Okay, so it cannot contain group 1 or ammonium ions. Right? So if you look at ammonium chloride is soluble, but it contains ammonium. So this one we're using titration actually. So A is out. Okay. Then again, we ask the question, is barium sulfate soluble or insoluble? If your answer is insoluble, you're correct. So if it's insoluble, we use precipitation. Okay. So since this is precipitation, wrong. Third one, copper 2 sulfate. Copper 2 sulfate, is it soluble? Yes, it's soluble. Okay. Does it contain any group 1 or ammonium ions? No. So we use adding excess. Okay, so C is your answer. Then option D, right? Potassium chloride. Is it soluble? Yes. Okay. Does it contain group 1 or ammonium ions? Yes. Potassium, it contains potassium. Potassium is in group 1. Okay, so we are going to use titration for this. So D is out. The answer is C. Okay. Question 9. Table shows information. Okay, so we have to solve the table. So the salt that we want to prepare in this case is copper 2 chloride. Okay, it is in a solid state, but that does not mean it's insoluble. Okay. They told us that the method they use is adding excess solid. Okay. So what are the reactants that can be used for adding excess? Acids plus insoluble salt. Okay, we have HCl here already, which is your acid, hydrochloric acid. So we just need to think of an insoluble salt that contains copper. So there are two answers for this. You have CuO, copper 2 oxide, which is solid. And you have copper 2 carbonate. Okay, so one of these answers are correct. Next, if we look at the formula of reagents used, we have potassium hydroxide and nitric acid. Okay, so this actually forms what salt? Potassium nitrate. Okay, and we want the salt to be a pure sample, a pure and dry sample. So the state has to be solid. Okay, so KNO3 solid. That's the salt. And because this is soluble and it contains group 1 ion, which is potassium, we'll be using titration. Okay. Final one, the formula of salt is lead-2 sulfate. Okay, PbSO4 lead-2 sulfate. If you look at the solubility table, right, lead-2 sulfate is insoluble, which means we directly go to precipitation because it's an insoluble salt. So the method is precipitation. And then what happens after you mix the mixture together? You have to filter it, right? So filtration also. Okay, so precipitation and filtration. Then the formula of reagents, there are two types. You can have a soluble salt and another soluble salt. Or you can have a soluble salt and an acid. Okay, so up to you guys. So if for me, I would choose an acid lah. So H2SO4. Because you need to contain SO4, which is sulfate. So the acid I chose is H2SO4. And then for lead, usually if I want something soluble, I straight away pick nitrate lah. Because nitrate is definitely soluble. So lead-2 nitrate. Okay, just make sure that the numbers are below. Okay, numbers are at the bottom. Okay, now I move on to the class details. So if you found this session helpful and then you want to join my tuition class, I actually give 20% off your first month to the first 5 students who enroll this month. And now there are currently 2 spots left. Okay, so not 3 spots, but 2 spots left. Okay, so I open slots for Sec 3 and Sec 4. For Sec 3, I have a new class which is on Sundays 3 to 5 p.m. Okay, so if you're interested, you can sign up via this link, tinyurl.com/sign-up-chemistry-LCH. Okay, and then if you are Sec 4, I actually open a new class on Tuesday. Okay, if you're interested for a Tuesday's class, Because Sec 4, right, you have 6 more weeks to paper 2. So think of this like a final revision. So if you are Sec 4 and you want to secure your A1 or A2, right, you can sign up for this final revision class, which is on Tuesdays 8 to 10 p.m. Okay, it's 6 weeks to paper 2 and 8 weeks to paper 1. Okay, this is on Tuesdays 8 to 10 p.m. If you are interested, you can also sign up via this link. Okay, tinyurl.com/signup chemistry LCH. Okay, if not, can you guys take 2 minutes? Can I ask you guys to take 2 minutes of your time to fill up this feedback form so that I know how to improve, future classes? Okay, then at the same time, if you guys have any questions, you can just send them in the messages.